Good morning to everybody. I will speak today, as announced, about the thermodynamic aspects of the molten salt reactor fuel. But I will try to make the presentation a bit like, overview, the general thing, linking thermodynamics with properties, and try to show how useful the properties can be with respect to design studies of the reactor. So actually, I will direct the presentation more to molten salt reactor, but you can, of course, the principles and the background behind can be applied to any reactor concept. So I would first start who actually in here who has dealt or deals with thermodynamics. Are there few hands? Okay, I would expect at least 1, 2, 3, 4, 5. Elisa, are you not? Yeah, okay, 6. Sarah, 7. Okay, very good. So yeah, I need to know, because I need to know whether I should make it 1.5 hour presentation or shrink it to 15 minutes only. So now I hesitate actually. But anyways, this is my outline. I would like to address, motivate why thermodynamics. Then I will have to say a bit of theory about some laws of thermodynamics. There are actually 3 + 1, so that would be 4 slides. Then I will speak about the Gibbs energy function, how we get the experimental data to calculate the Gibbs energy function, and then how is this Gibbs energy related to all sorts of calculations and applied to phase diagram studies. And at the end of my talk, if time allows, and I hope so, I will try to show the application of having these phase diagram assessed and actually having this thermodynamic database developed in a view to optimize the fuel for molten salt reactor, and to show you also how we can determine, once optimized composition, how we can determine the fuel properties. So that's the outline. Let me say a few words at the beginning. So why thermodynamics? The answer is thermodynamics tells us the equilibrium state. So that's the state that the nature tends to become to. And once it's reached, then you can assume that the system of any kind of study is in equilibrium, and that remains like that. So it will tell us with respect also to external conditions, and these conditions are what you can imagine: a temperature or pressure, or if you look at molten salt reactor fuel, which is either fluoride or nowadays also considered chloride salt, so that would be also the potential of fluorine. So for instance, this determines whether you will have uranium fluoride as tetravalent or trivalent, or whether you will have a mixture in equilibrium. So these are the external conditions, and the thermodynamics tells us, with respect to these conditions, to these properties, or to these variables, what will be the equilibrium state. And of course, what I cannot miss, and I will come to this several times during my talk, is the Gibbs energy, because the Gibbs energy determines the equilibrium state. And it's given that let's say the system that has the lowest, or the state with the lowest Gibbs energy, is the one that is the stable one. So it's calculated with enthalpy minus temperature multiplied by entropy, but as I said, I come back to that a bit later. So an example can be water, which is not really a component of molten salt reactor, but it's a component that everyone in the room is aware of and uses in a daily life. So if we calculate the Gibbs energy of liquid phase, so liquid water as function of temperature, and the Gibbs energy of the gas, we will see that at lower temperatures, actually this is the at 1 bar pressure, this is calculated at 1 bar pressure. So at 1 bar pressure, this is the boiling point, which we all know is 100 degrees C, 373 Kelvin. So below that, the liquid phase, the Gibbs energy of the liquid phase is more negative than of the gas phase. So therefore, the liquid phase is the equilibrium state. And above the temperature, the two lines cross. Actually, at the temperature they cross. And above the temperature, the gas phase becomes more negative compared to the liquid. So the vapor is formed, and the steam becomes equilibrium. So this is a very simple example, but it gives you the idea about why the Gibbs energy is important. But as I said, I will kind of grade it up a bit with the complexity of the system. So I told you thermodynamics is equilibrium state, but we have to be aware that we don't always, in a real life, reach the equilibrium state, and also the materials that we study don't always become to that state. So it tells us whether the process, a reaction, for instance, can or cannot occur, but it will not tell us whether it will or will not actually happen in a real situation. And I always have this example of this equilibrium reaction. And if I would ask you in the room, which side of the reaction is actually at room temperature equilibrium state? Is it the mixture of hydrogen and oxygen in a gas phase, or is it the molecule of water? Someone says left or right. Who gets it gets a beer. I know it's the day after the conference dinner, but no beer for tonight. So it's actually the water molecule, but we know, so that's the stable state. Did someone say it? Okay, you have a beer. Very good. So that's the stable state, but we all know that actually if you mix now in the room, if I would have a vessel and I would put hydrogen and oxygen, they would also coexist in a gas phase. And this is actually that there is the kinetics or the kinetic barrier involved. So if you look at the energy, although the water is the stable state as we all agreed, so that's less, actually it's more negative in terms of the Gibbs energy than the initial state. But you have to go over this barrier. And the barrier, for instance, in this case is a small spark, ignition. If you ignite it, if you add extra energy or maybe even ultrasonic shock or something, it will react. It will overgo through this barrier, which is this kinetic barrier, and it will become the water. So this is the thermodynamics, and this is the kinetics. So that's a bit to give you an idea how one has to distinguish. But in case of molten salt reactor fuel, we are speaking about fairly high temperatures where the phonons also interact quite fast, the vibration, etc. We are in molten state, so normally the thermodynamics is the dominant key player at those temperatures. So we can actually, while doing thermodynamics and thermodynamic modeling, we can very nicely assess the actual real state. So let's go quickly through the laws. So I cannot do the presentation without the laws, especially at the summer school. So the first law says that the energy of a system cannot be produced or cannot be destroyed. So that means that actually if you have a system, you take part of the energy, the balance is always the same energy, no matter whether it's heat or work done on the environment by, for instance, gas expansion. It's conserved. So that's the first law. The second law tells us, okay, there is again a nice definition. I will not read it, but it tells you that the heat flows always from, in simple words, from hotter to colder. It's very simple. I mean, we all know it, but it's that's the basis of the second law. And because of this phenomena, an entropy has been established or formulated by Rudolf Clausius. And the entropy is actually a measure of a system disorder. What does it mean? That means that the higher the temperature, the higher the system disorder you have, and the system tends to be with respect to equilibrium, the system tends to have the maximum entropy possible for a given temperature. An example can be a mixture of two gases, which are two inert gases. So I choose helium and neon. The reason for having the two gases is that there is no interaction, chemical interaction. So it's a very nice example to show if you mix the two gases, helium and neon. So let's say 1 mole of helium, 1 mole of neon, to become 2 moles of 50% mixture. So if you calculate the entropy of, or let's first say, what happens if you mix these two gases? They will not. I mean, if they are in separate vessels. Trapped helium, trapped neon, of course it's only helium and neon. But when we put them together, they will not stay separate. They will mix. And that is also the driving force is the entropy behind, because then you will have, the system will tend to mix completely and have different combinations in terms of mixing the two independent gases, or chemically independent gases, let's say. So if we calculate the entropy of actually 1 mole of helium and 1 mole of neon, we get the sum of 322.8 joules per Kelvin per mole. And if we mix them, there is this mixing phenomena behind, not chemical reaction, but mixing phenomena. So if you calculate the mixture, actually, we get a higher entropy. So this is a proof that actually the entropy is higher, and that's related to the equilibrium state. So that's the second law. And the third law is, again, related to the entropy, but it states, I told you on a slide before, that the entropy is actually, the system tends to maximize itself with respect to entropy. But here it says that at 0K, and for perfect crystal, that's a condition that must be kept, the entropy is 0. I told you that the entropy is proportional to the disorder of the system. So the example I showed you before of a temperature, at room temperature, for instance, two gases which are very mobile, or the atoms are very mobile. So there's a zillions of combinations, so the entropy is, of course, very high. But if you have a perfect crystal, which has no defects, so that's perfect crystal. And so that means you have only one possible microstate, which can be achieved at 0K. Putting this in a relation of the entropy definition, which is the Boltzmann constant times natural logarithm of the number of microstates, this becomes, of course, 0, and the entropy becomes 0. So this is very important aspect in thermodynamics. So the entropy is actually absolute quantity, because at 0 it is 0 for perfect crystal. And the zeroth law is that if you have two systems or three systems, and system 1 with system 3 and system 1 with system 2 is in equilibrium, in thermal equilibrium, for instance, that's also that there is a thermal equilibrium between the. It's very simple, but the thermodynamics uses these four laws, and then there are less or more complex equations, and it just works. So then we have also equilibrium between the two systems which are independent. So what have we learned? I mean, of course, we can put this in equations, but we can also, what is the practical info for someone who doesn't deal with thermodynamics and is a normal human being, let's say, or we are all normal human beings, although we also work with thermodynamics. So the first law actually tells us that you will never win. You can only draw. I mean, you don't win any additional energy. So that's, well, it's a bit frustrating that we cannot win. But still, if we can tie with someone, that's fine. But then we have a second law which tells us that we can draw, but only at 0K. Well, that's even more frustrating, because, but still, we have an option. But then the third law tells you that you will never reach 0K, which means that becomes completely frustrating, because that means that the lesson learned is that we can only lose, which is very bad. But on the other hand, if you do something wrong in the lab, you can tell your bosses that actually you followed just the laws. So it's not bad to have this excuse. So that's yeah, okay, that's just a bit. But let's see what properties, and that comes more interesting with respect to reactors, what actual properties are linked to thermodynamics and the Gibbs energy itself. So the properties are, I mentioned the first one, but an example of water, boiling temperature. That's typical thermodynamic quantity I showed you on the graph. The same works as for melting point, so you will have phases that you have to consider the solid and liquid, and then when the Gibbs energies cross, if I take a very simple example, that's your melting point. Then you have the any transition temperature. That can be melting, it can be phase transition from alpha, beta phase of any solids. Example here is very complex, well, it's not a complex system, it's one element, it's plutonium. But what's nice on plutonium is that it has a lot of structural modifications before it melts, actually. It has 6 modifications, and so also some properties changes according to these to the temperature and actually the actual phase that is the stable one. So here, for instance, you see the significant drop between density of alpha plutonium to beta, gamma, delta, and then increase for epsilon phase. Then the vapor pressure is important quantity, and also very important for molten salt reactor technology. It determines the volatility of the fuel, or for instance of the fission products, which may or may not be dissolved in the fuel. Another property is heat capacity. It speaks for itself. It's the amount of it's the capacity of a material to absorb heat before it, for instance, heats up itself by certain amount of degree C. So Of course, this also the knowledge of heat capacity tells you what will be your buffer zone, for instance, of a molten salt reactor fuel, if you would, sort of speaking, lose the control of temperature, and it would heat up for any reason. So that would give you the time response, answer, let's say. So those are example of properties. Another example is the enthalpy. The enthalpy is the energy that is needed to heat up the sample. So if you plot, an example here is on thorium fluoride compound, which is misspelled. So that's thorium fluoride compound. So this is if you plot it from room temperature 300 Kelvin up to 3000. I choose here to go through both phase transitions. The first one is melting. Second one is the boiling point, the vaporization. So you see that according to the heat capacity, actually, as I will show you on an equation later on, you have with respect to temperature, the enthalpy increases, of course. Then you reach melting point. Then you have this kind of a jump. So all of a sudden, this is the amount of that's the fusion enthalpy that you need to add to the material to melt it completely. Then you have a liquid phase at a higher temperature. Then you are heating up again. So the enthalpy again increases according to the heat capacity of this time of liquid. And then you have a vaporization. So this is the boiling point, somewhere around, well, I see it from the angle, but I think something like 2000, 2020 Kelvin. And then after you add this big portion of enthalpy, of energy, of heat, then the gas phase is formed. So that's a bit explanation of the enthalpy and why it's important, but also this shows also how big difference there is in general between the heat of fusion and the heat of vaporization. And this is, for instance, why fire is well extinguished by water, because it's actually you cool it, but you also form for the steam, which if you would plot water here, you would have also fusion of melting temperature much lower than the vaporization, and this is the heat that actually you take from the fire and then you finally take down the flames. So that's that's the enthalpy. So all these properties are actually important for the reactor design. So that's of course why we have also big interaction between, let's say, the thermodynamics and the reactor physicists. We had also big collaboration, for instance, between the properties of the fuel and the neutronics, because of course there must be criteria, compromise of all criteria, not just to select the fuel that is the best from the point of view of properties, but it must also fulfill the neutronics, for instance, viscosity as a fluid dynamics, etc., etc. So it's a bit, but a lot of relevant properties I try to show that can be answered by having this approach of thermodynamics. So, as I mentioned already, well, I normally ask here who is this famous scientist, but if I have here Gibbs Energy, I think it would be very cheap beer. So yeah, it's Josiah Willard Gibbs. But that's important really to repeat that all these properties and their determination can be done by knowing the Gibbs energy. So it's also our task when we do thermodynamic modeling, phase diagram assessments, to assess all the Gibbs energies of all the phases which are relevant for the system, and I will show you on slides later on. And once you have this, you can determine all these properties. So that's important to that's the lesson to be a bit taken. So that's one of the few equations I showed today. You saw the first one, the one above. So the Gibbs energy as function of temperature is determined as enthalpy, again function of temperature minus temperature function of entropy multiplied by absolute temperature, and then the enthalpy. And why I show it also in a bit. I already mentioned the heat capacity with respect to the enthalpy. When you have this thorium fluoride enthalpy increased graph, I always mention the heat capacity. So the enthalpy is defined as, for nuclear fuel, we look at temperatures above room temperature. So it's defined at formation enthalpy of 298, so at room temperature, plus the heat capacity contribution. So it's the integral value of the heat capacity function, and the entropy is the absolute entropy. I told you, remember, entropy is not relevant quantity. It's absolute because of the laws of thermodynamics, that entropy at 0K is 0 for perfect crystal. So you have the absolute entropy at 298 plus the heat capacity divided by temperature and its integral value. So to sum up this, if we want to determine the Gibbs energy for a component, for a compound, let's take thorium fluoride, for instance, one compound, we need to have knowledge of formation enthalpy, absolute entropy, and the heat capacity. And we need to know, for instance, if you look at melting point, for instance, we need to know this for a solid phase and for the liquid phase, because only then we can compare the two Gibbs energies and determine, in this case, melting point. So that's the, and of course, we need to know the transition enthalpy and temperature of transition in case we look at transitions not only in a single phase, because that's this jump you saw on the graph, which is not related to heat capacity, but it has one given value at one given temperature. So these are quantities. So I would like to go through now to show you how you can determine these quantities in the labs. Of course, you can calculate. There are techniques how to calculate these quantities nowadays with supercomputers, by molecular dynamics, by ab initio. But for any license and for the correctness, you will always have to demonstrate this experimentally. So it's important to not to abandon this area. So the first quantity, an example, one slide, formation enthalpy. So in thermodynamics, the formation enthalpy at 298, I mentioned it's not the absolute quantity. It's relative quantity. So it's more or less, so speaking, undetermined with respect to to the energy. But of course, we have to constrain it. And in thermodynamics, we pose that the formation enthalpy at 298 for elements in their standard state is 0. This is important because that's our floor from which we reference. So actually, if you look at, for instance, formation enthalpy of plutonium trifluoride as an example, one of the fissile component in molten salt fast reactor, for instance, studied in Europe. So, as I said, the formation enthalpy of this compound, as is defined in thermodynamics, as we calculate with, is related to the elements in their standard state. So, in other words, if we measure this reaction, plutonium metal with the reaction with fluorine gas in, of course, stoichiometric amounts to form plutonium trifluoride, we determine the formation enthalpy, which is exactly the reaction enthalpy of this. For this, we have, for instance, a method of combustion calorimetry, which is a vessel filled with. So in this case, it will be okay. This is the design of a certain vessel, but the idea is you would put a plutonium metal into this vessel, and you would fill it with a high bar pressure of fluorine gas, maybe 100 bar. I mean, to make sure that you have really enough fluorine to react all the plutonium, the best even in several excess amounts. And then when you equilibrate the system adiabatically, you ignite this, let's say, it's not a mixture, or this system, the plutonium metal and the fluorine gas. And then you measure the response by either measuring the heat that goes out or measuring the temperature increase of surrounding water. So if you have the system calibrated with something known, you can determine the heat of reaction, and thus, if the reaction corresponds to the heat of the definition of formation enthalpy, as in this case is, then you get the quantity. So that's how it's one way how to determine formation enthalpy. If you look for the mixtures, for instance, the idea is very similar. It's always that you have to find the solvent where the mixture can dissolve. So in case of lithium-thorium mixture as a key system for molten salt reactor, or thorium-based molten salt reactor. So you would have to probably look at diluted hydrogen fluoride aqueous solution at certain temperature, maybe a bit elevated at 50 degrees. And then you would dissolve first the mixture that you want to study. Afterwards, you would dissolve, or before, doesn't matter, in another experiment, a lithium fluoride pure and thorium fluoride pure separately, so 3 experiments in total. And then you would, from the value of the mixture, you would subtract the values of pure components, and then the difference would give you the enthalpy of solution, enthalpy of mixing. So that's the example of formation enthalpy. Has the absolute entropy as the second quantity. So this is determined. We take the advantage of having this quantity as absolute quantity with 0 value at 0 K, or more or less. So we use the low temperature calorimetry, adiabatic calorimetry, or physical property measuring system, which is semi-relaxation method. And the idea is to measure the heat capacity from 0. Okay, we will, as you learned, we will always lose, so we never reach 0 K. But close to 0 is enough to have the whole integral characteristic of the heat capacity over temperature. And this I show, for instance, example measured in our lab of uranium trifluoride compound, which is one of the fuel components, because that's actually a trivalent uranium fluoride, which is used to control the corrosiveness or redox potential of the sol if you have uranium tetrafluoride as a key component. So this was measured, and okay, at very low temperature, just by matter of interest, we measured the magnetic anti-ferromagnetic transition related to uranium atom. But then we had this nice heat capacity function, and the Cp over T integral towards the room temperature gives us the absolute entropy. The method is on the picture. It's adiabatic calorimeter installed also at our institute in Karlsruhe. Okay, it's no longer working. We are now switching more to PPMS, but especially for the fact that you had to use here gram quantities, which is not very practical when you deal with nuclear materials and also with higher actinides after plutonium. So then the PPMS is much more, well, it's better because you can use lower quantities. But the method is very simple. You just make, the method is simple. You add the heat to the sample, which you have to know how much. That's easy to measure. And then you just measure the how much by the delta T, by how much it increased, and that is proportional to heat capacity. What is not simple is to keep the adiabatic conditions. So therefore, this is the vessel where is the sample, and you have these, it's all in a vacuum. It's of course cooled down depending on what temperature you want to measure. But then you have these two thermal shields which have like a coil of a small wire which is heated and compensated. It compensates the heat, the temperature in between. So there is no flow of heat other than just to the sample. So it's a bit tricky, but the idea is that's important. So that was the entropy and formation enthalpy. Before I go to heat capacity, there is also transition enthalpy. So this is, for instance, measured by probably the most common experimental facility is the classic differential scanning calorimetry, the DSC. This is a scheme of a detector. Normally, you have two crucibles. This is surrounded by a series of thermocouples that measure the they measure, that's bimetal, so they measure voltage, but that's converted by certain, taking into account the geometry into a heat flow signal, which flows between the crucibles. So one crucible is always a reference crucible that's empty normally. The other crucible is filled with a sample. And if you look for the transition enthalpy or phase diagram equilibria, solidus liquidus points, I will show many during my second half of presentation. So you normally have a constant heating at 10 Kelvin per minute. If nothing happens if there is no melting, no transition, there is constant increase of both crucibles. The heat flow may be quicker on the reference crucible than with the filled crucible, because of course the heat capacity is also different. But there is a smooth profile of the heat flow between the two crucibles. But once you melt the crucible, while the device is programmed that it still heats. So you remember my graph with this jump on the enthalpy. So the sample that melts, or the crucible where the sample is, and when you reach the melting point, of course you need to add first this enthalpy of fusion, this jump on the enthalpy graph, before it can heat up again. And in that case, that crucible becomes delayed compared to the reference crucible, because the reference crucible is heating up constantly as programmed. And there you observe a peak on the heat flow signal. So this is a typically observed peak. This is actually, by the way, measured by, I think, Elisa sitting here. So that's the lithium. That was lithium thorium fluoride mixture. It's one of the interesting composition for molten salt fast reactor, because it's close to these eutectics. But it was also important quantity for us to perform the thermodynamic modeling of the lithium fluoride thorium fluoride system, which I will show you later on also in this presentation. So that's the peak, which relates to the melting point. And so the onset of the peak is the melting point determination. And if we can quantify this peak with a internal reference, where we used silver reference material, we can also quantify the area of the peak, which is proportional to the enthalpy of fusion. So from this experiment, actually, we can get both the enthalpy of fusion and the temperature of the fusion. And the heat capacity is the I think last on the list from the properties I listed as relevant properties for the Gibbs energy. And this is you can also use DSC. Okay, I will have next slide on that. But you are using also a different calorimetry technique, which is a drop calorimeter. But the technique is based on the fact that this is the detector. So this is the tube which goes up and down to the furnace. So now it's lifted up, and you have a sample initially before the experiment. You have a sample here at room temperature. And then when you equilibrate your signal in the detector, again the heat flow signal, you drop the sample and you observe, you measure the enthalpy increment that is needed to heat the sample from room temperature to any temperature that you have in your furnace, in your calorimeter. So of course, if you do this for different temperatures, as shown on this example, you get directly the enthalpy as function of temperature. And then if you continue above melting, this is example of cesium fluoride. Cesium fluoride is one of the stable form of cesium fission product, which will stabilize at the fluorine potential of molten salt reactor if you use fluorides. And then you could clearly see that actually you are heating up constantly, and then once you reach melting point, you have this jump, and then you continue again increasingly with the enthalpy. So that's the enthalpy, but the heat capacity by definition is the derivative of the enthalpy with respect to temperature. So once you have the enthalpy functions, you can get the heat capacity, and in this case of both liquid and solid. Plus, if you take the difference between this point and this point, you get again the fusion enthalpy. So that's another independent technique to get the transition enthalpy. So that is also important to benchmark with different techniques. If you look at something and you want to have a quality assurance, for instance, on the data, which you want to then provide to regulators to get your license. So this is also an example that it's always good to have benchmark between institutes, but also within an institute if you have two techniques, and it's very relevant, important. So that was the drop, and then the DSC is more or less the idea there is that you are what you show here is the heat flow of again between the two crucibles. In this case, the program is not constant heating, but it's in steps. So you equilibrate temperature, then you heat it up with 20 Kelvin, for instance, typically. Again, equilibrate several hours, and you go on. So this is the temperature. Those are the steps on temperature. And with each heating, there will be certain peak on the heat flow signal, because there is that depends on the difference, and this is proportional to the difference between the heat capacity of the sample crucible and the reference crucible. So this method requires measuring actually blank known material with heat capacity called reference, and then the unknown heat capacity, the unknown sample with unknown heat capacity, or sample with unknown heat capacity. So that's quite time consuming, but it's another method to use it. What I didn't say, important when you study high temperature properties of fluoride or chloride salts, you have to encapsulate the samples. This is also why it makes it experimentally more difficult, but it's important. First, at very high temperature, they are not that volatile, but they still evaporate, so you would lose the sample. So of course, something you want to avoid. But combination of those vapors with maybe a bit of moisture in the environment, although you use argon also, and with high temperature, you will have it very corrosive. So that's something you want to avoid as well. You want to avoid deposits. So that's the experiments. Are there questions to that? Quick questions, or I go on? 2 more seconds. No questions. Okay, I go on. So this is the what I showed up to now. I showed you how to determine, with help of experiments, the Gibbs energy of compounds. Now we go to the mixtures, which becomes a bit more complex, and I will start with the binary mixtures. So understand mixture. If you look at this phase diagram, this is lithium fluoride, thorium fluoride phase diagram. You have various phases here. You have lithium here, thorium fluoride here, or lithium fluoride here, thorium fluoride here, and then you have 4 intermediate compounds. So what I showed you up to now is relevant to the 2 end members plus the 4 compounds, to determine the Gibbs energy. But there is also one another phase, if we neglect now the vapors, there is the liquid phase, which is actually quite above melting and above the liquidus in the phase diagram. But this is the liquid phase. So now, of course, if you want to vary all these Gibbs energies, you have to consider also this liquid phase, and you have to describe this liquid phase. And it's a bit more tricky because, as you see, the liquid phase is it's a continuous field. So even if you measure the properties of one composition, the property will change in another composition, and it actually gives you infinite amount of measurements which are impossible. So therefore, you define the Gibbs energy as a Gibbs energy of solution, which is still based on if you have solution of lithium fluoride, thorium fluoride, so it's still based on the Gibbs energy of the lithium fluoride and thorium fluoride in this case. But then there is this delta G mixing, which is related to when the liquid solution forms, when it's stabilized. So when this field is formed from lithium fluoride and thorium fluoride. And this is then defined as a function of activity. Activity is related to vapor pressure. So you can measure the vapor pressure, but again, it comes to the same point that if you want to describe this part, you would have to describe all the compositions. So therefore, you have thermodynamic models that actually are used to it. So if you write this part, this mixing part, there's something exists like Rolle's law. Rolle's law says that if you have ideal solution, and I tell you it's not the case of any molten salt liquid solutions I've dealt with, so that's not the case, but if you may have an ideal solid solution, and then the activity is equal to the composition. So then it's very easy. You don't need any thermodynamic models. You just write activity equal to composition. Then you follow the Rolle's law. So that's actually this dashed line, which is the relation between the composition from lithium to thorium, for instance, and the activity from lithium to thorium. And then you are done. But if in real case, which is normally the case, the activity is not X. So then you define something like activity coefficients, and then the delta G mixing becomes, again, ideal mixing term plus the excess term. Excess term is defined by these by these activity coefficients. Gets a bit complex. The important message here is you need to apply certain thermodynamic models that describe this part, which is then defined as mixing enthalpy. That's the energy that is related to this mixing of lithium fluoride, thorium fluoride to form the solution. I showed you this example of the solution colorimetry, for instance, between lithium thorium. But that you may measure, but again, infinite composition issue. But you will not measure the excess entropy because entropy is not related to heat, and that's difficult to determine. So you need some models. And I will not describe the model because it will be too complex. But I will show you, for instance, an example, simple system, lithium fluoride, potassium fluoride. The reason I choose this one is very simple eutectic system. I start with the first step. So if you want to plot or assess the phase diagram using the Gibbs, you need to know, to assess this fully, you need to know lithium fluoride, Gibbs energy of lithium fluoride solid, lithium fluoride liquid, potassium fluoride solid, potassium fluoride liquid, and the liquid phase in between. So how do? We measure, since we cannot determine everything, we can measure lithium fluoride and potassium fuel, but not the liquid phase, so we do the thermodynamic assessment. So what we do, for instance, we measure few data points which are related to Gibbs energy, for instance, melting points, so in this case, solidus, liquidus points. And in the first step, we try to say, okay, we do the measurements, and then we first say, let's treat the liquid solution ideally. So what happens? That's what the result is. If you treat the liquid solution ideally, and I told you ideal solutions are not really in this case, you have the shape of the eutectic, but the temperature of the eutectic is far above the desired 760 degree, which is by experiment. So what you have to do, you have to play with the delta H mixing and maybe delta S excess, which are the excess Gibbs energy properties. So we do it. For instance, we measure the delta H mixing, which we did in this case also. So that was the, if we put it in very simple polynomial formalism, we get quite nice agreement already. So the temperatures are now 22 degrees off, which is still something, but much less than 150 from the previous picture. And also the liquidus point, liquidus line is not very reproduced here. But the match is not too bad, it's getting there. But that means that we cannot just use the delta H mixing, but we have to also optimize excess entropy or excess heat capacity or other properties. But in this case, we did the excess entropy, and then we optimize it so far that we get the perfect fit. So this is just a simple practical practical information or example on how the phase diagram is assessed. And then if I go to the final equation of the delta G mixing, so it's the ideal term plus these two enthalpy and entropy terms. So how do we do it if we have a more complex system? So I will stay with lithium fluoride, thorium fluoride phase diagram. So first of all, you saw the shape at the beginning. So you know there are intermediate phases. So first of all, we have to identify all these phases. That is important. We do this with series of XRD measurements. We can prepare different compositions. We can also do quenching experiments because there can be also high temperature phases which are not stable at low temperature. But the idea is to have the idea is to have idea about the intermediate compositions. In this case, 4. So we know that we have 4 compositions. So we plot the X phase diagram. We just put the lines. In the next step, I would measure the solidus liquidus data by the DSE, and we kind of we define ourselves based on the experimental input where the liquidus line will be. So that means that in this case we know that these intermediate phases cannot be stable more than the liquidus line, so we can just simply trim it. But this is of course not thermodynamically in accordance with thermodynamic laws. So we can look at these different indications of equilibria, which are probably straight lines, which we can draw. And these straight lines are actually afterwards related to each of the reactions. Something can be eutectic reaction, something will be peritectic, but each of them will be related to, by looking at the law of thermodynamics, to one of the compounds. So we can trim it again, and then in the last step we have to follow this phase rule, which then gives us the idea of the phase diagram. So this would be our idea of phase diagram, and then if you do the full assessment, we get actually this. So this is calculated phase diagram. You saw it already on smaller picture, but exactly it reproduces the ID that we get from combining the measurements. And actually this slide also shows you that the idea is not only to take the DSC data, the solidus liquidus equilibria, which are shown here, but also the enthalpy of mixing determined experimentally, fusion enthalpy determined experimentally, and all this is considered, and you do the description of the thermodynamic model of the liquid solution as best to reproduce not only the shape of the phase diagram, but also these quantities. So this is fusion enthalpy of this point, which is also very often considered solvent for molten salt fast reactor. So if we have the phase diagram, what can we get? What kind of information can we get from the phase diagram? And this is maybe more practical. So I take here is a point. It's a red sphere. So at this point, which is this composition, 78% lithium fluoride and 22% of thorium fluoride. So at 1000 Kelvin, what can we determine from that point? So first thing is what is the phase in equilibrium? So it's in a liquid phase in a homogeneous region, so it's only liquid. What will be the melting point, not of the temperature, but what will be the melting point of the composition? So if you go down with the composition straight down, you hit the liquidus line, and that's the answer. What is the first crystal formed? So this is important. For instance, if you have a system with plutonium, you want to know whether the first precipitate would be plutonium rich or uranium rich, like fissile material rich. So this is an example what you can get. So if you go down, you hit this two-phase region very shortly, and it's lithium fluoride. Further, what is the boiling point? You can calculate the boiling point, as I said. You can calculate the heat capacity. What will be the heat capacity of this composition? Again, important, as I explained at the beginning of my talk. You can calculate the vapor pressure, the total quantity, how volatile it is. So in this case, it will be not that volatile, but we can also look what is the level of what we call incongruency. What is preferential to vaporize? Is it lithium fluoride or is it the actinide component? And in this case, you see that there is an order of magnitude different between lithium fluoride and the first thorium fluoride gaseous mixture. So this is, for instance, this kind of information is important when you look at the retention of fission products, because there really you can look if you have the full assessment, also considering the fission products, which is not trivial, which is far from trivial thing. But then you can assess whether cesium fluoride will be, or iodine will escape, or will be trapped in the fuel with respect to temperature. Next one is you get all the thermodynamic quantities, which are not more relevant for the ones that deal with the models. And you can get the activity coefficients, which are, again, it's measure of stability of the system, more or less. So that's and also important for if you do electrochemistry. There'll be talk later on by Sylvie Delpech. I'm pretty sure she will hit those activity coefficients, the electrochemistry, because it's important, for instance, for cleanup, reprocessing of the fuel. So that's it. But I showed you, I jumped from phases, single phases, to binary system. And now it comes to the multi-component system, because that's what the fuel itself is. So if you, I think there was a nice, I wasn't here yesterday, but I'm pretty sure that this has been introduced maybe in different slides. But this is more, the idea of this slide is to show that, or remind you that the fuel, the fresh fuel, is already multi-component system, either ternary compounds, ternary system, lithium, thorium, uranium, or even quaternary with lithium, thorium, uranium, and transuranic fluorides or plutonium trifluoride. You can imagine if you form fission products, it becomes even more and more complex. So the message here is that fuel is multi-component system, so we have to also develop the database that it doesn't cover just phases and binary systems, but it covers also the multi-component system. So how do we do that? Because the binary system, the assessment I showed you, there are mathematical formalisms. I will not go into detail to that. I'll just show you the graphical kind of scheme, how you do it. So this is an example of Flyneck system. Flyneck is lithium fluoride, sodium fluoride, potassium fluoride system. And to determine the full phase diagram, for instance, to look at the lowest ternary eutectic, which is actually here, but you need, the basis is to have the binary systems. So what I showed you in slides before, how to assess, for instance, the lithium fluoride, potassium fluoride system, or lithium fluoride, thorium fluoride system, you do all these 3 binary systems here. I choose this example because those are all rather simple eutectics. Okay, this is the one I showed in detail, but this is then sodium-lithium with only partial solubilities of lithium in sodium and even lower of sodium and lithium. Of course, this is logic because sodium is bigger than lithium, so that's quite well logic. The same for potassium-sodium, and then what you see here. So the rest of so you have the description based on experimental data in the first step based on the edge of the ternary system, so the binary systems. So these are this system, and then the rest is extrapolated by mathematical formalism. So actually the data of the liquid solution of the 3 systems are extrapolated by the mathematical formalisms. You might have heard about Muggiano, about Kohler-Top methods. As I said, I will not go to the detail to that, but that's the philosophy behind. And this, to explain you, I don't know if you are not that fluent in reading this phase diagram, because I will show one example at least of optimizing the fuel. So you will see many of these phase diagrams. So this is a liquidus projection because we are looking at melting point. So this is a liquidus projection of fuel of several isotherms. And so the blue are the lowest temperature, and then of course the higher the temperature, the bigger spread you have in your molten area. So if you plot all these lines together, you get this idea about where is the lowest melting point. In this case, it starts at ternary eutectic, and then actually it increases towards the 3 eutectics of the binary systems, and of course the highest melting point in this case is, I think, they are fairly similar. But that's the liquidus projection. So it's very nice representation how to look at the melting point and also how it behaves, how it reacts with respect to composition. And this is extremely important. So in this case, this is the lowest melting point. So how to use it in practice? So consider we have the thermodynamic database, and we have it. So we developed it in this way. So my first example is, and maybe I will show just one, depends on the time. Is the optimization, which we did in the last molten salt reactor-related Horizon. No, that was not Horizon. It was FP7 project in Evolve. It was the optimization of the fuel for MSFR, for the most fast reactor. And you know that there are 2 fuel options, and one of them is based on lithium fluoride, so lithium-7 with thorium fluoride as fertile material, and the plutonium trifluoride as fissile material. And for this, we need to have the full thermodynamic database. So again, I come to the point that you first need the binary subsystems. So it is the lithium thorium fluoride, no need to say something about it, already mentioned. Lithium fluoride, plutonium fluoride, which is a simple eutectic system. We have even nowadays added more points here. And then there is the thorium-plutonium. So those are the variations you have to assess, and this gives you the basis, or this gives you the basis for the database, but the database of the ternary system. But of course, then you need also validation by experimental points, and these results you can use in optimization. So something about the criteria we have to respect. I told you it's lithium, thorium, plutonium fluoride ternary system. So the initial idea was to use the lowest, the solvent of the lowest eutectic point here, 77.5, 22.5 atomic percent, which melts at 840 Kelvin, and dissolve neutronically desired 5 molar percent of plutonium trifluoride. So if you look at, there has been also some measurements performed in Oak Ridge, but also by our Russian colleagues. So then if you look at the solubility of plutonium trifluoride with respect in these two melts, so one of them is almost identical or close to this selected matrix. You need, if you look at 5 mole percent and you hit the line here, you need something like 935. It's 935 Kelvin melting point, and that's the melting point. And you would need even higher temperature for a certain temperature margin. So now the question is, using this database, can we optimize? And these are experimental results. So that's, of course, it's and also the line is the calculation based on the thermodynamic database. So there's no way around. But can we find a different? Can we play, for instance, with a lithium thorium mixture to find a lower melting point? So that's what we try to do once we had this database assessed. So more or less, this is the phase diagram, the full phase diagram. And if we plot this again, the liquidus projection, we find it's very nicely drives you to the lowest melting point, which is very low. I mean, it's 935 was before, but this is much lower. But if you look also at the concentration, and this is why it's important, it's much less of plutonium trifluoride. So of course, this is not that you cannot use, because that's far less than 5 molar percent. But what you can do is, once you have the database, it's really easy to calculate around it if you have the right software. You just calculate the pseudo-binary system, because this system respects everywhere these 5 molar percent of plutonium trifluoride. Yeah? So if I put it as Tx, temperature composition phase diagram, you will see that if this was the initial fuel composition, if you add 5 molar percent into this 77.5, 22.5 solvent, you get this composition, which had this 935 Kelvin. That's the point A. Point A is here. Now you see that only by playing between lithium fluoride and thorium fluoride ratio, going somewhere here to this composition point B, which is here in this valley, you can gain the temperature drop by more than what, 60 degrees. So this was very important, very interesting results that we discussed also with our colleagues in CNRS that did the neutronics and the reactor design behind. So that only shows you that it's very it's long way to get to the database. It's quite some effort, but what is not. But once you have it, you can profit a lot. Of course, you have to validate this, and we did validate. So we had quite nice experimental match with this particular phase diagram. But it gives you the idea where you should be going. So that was one example. I have time. Yeah, I think I have time. So I take another example, and that was actually this was done in collaboration or informational exchange for sure between Victor, our colleagues in Kurchatov, and us. So that is about the optimization of the fuel for Mozart concept, or maybe not optimization, but looking whether, with respect to melting point, we need all three components to dissolve plutonium trifluoride and to keep the melting point low enough. So in this case, maybe that's changed already in the course of time, but at the time when we did this study, the lithium fluoride, sodium fluoride, beryllium fluoride was proposed for the solution of plutonium trifluoride. This design is actinide burner, so you don't need to dissolve that much of plutonium trifluoride. The characteristics, the summary of the data that are relevant to what I want to say are here. The proposed inlet temperature 873 Kelvin. So that means with 50 Kelvin safety margin. Okay, this is of course matter of discussion, but you have to have at least something. So let's put this as our criteria. Outlet is higher, so that's no problem. But then this is the concentration we have to keep. I mean that's how the reactor works. it must be at least 1.3 mole% of plutonium trifluoride. So we have to put this somewhere in a fuel composition. And now the idea was, do we need beryllium fluoride as a third component? Or can we just have lithium sodium? Or can we have lithium beryllium and not sodium? Or can we have sodium beryllium and not lithium? Et cetera, et cetera. So what we did, we are not a ternary system, but we are a quaternary system. And quaternary system means that you have to assess not 3 phase diagrams, but 4, but 6. So these are all listed here. There is nothing so particular on any of them, just that somewhere with more, some with less data points. I think the one that was assessed with almost no data points was this beryllium fluoride, plutonium fluoride. So this was based on some proxy systems between beryllium fluoride and cerium fluoride, for instance. And but we got somehow to the database, which we used to give a basis for the full assessment. So first we look on the lithium sodium. We avoid beryllium. So as I said, beryllium is neutronically extremely friendly compound, but at high concentrations, for instance, it causes high viscosity. So because it turns to form polymers, etc., etc. So of course, that's always a question. And once we have the database, we can just play around. So first we did the avoiding beryllium. This is summary of our criteria. And again, we plot the full phase diagram, and we find the lowest melting point here, 893. So that's the very lowest melting point of this ternary, and that's enough. I mean, it's much higher than what we set to our criteria. So we don't have to look farther. Even if we would respect the concentration criteria for plutonium trifluoride, we would plot this phase diagram, and the temperature, of course, must be higher than this one because this is the lowest ternary eutectic. So the liquidus here is even higher. So the answer here is no. I mean, lithium sodium will not solely replace beryllium or mixture containing beryllium for this purpose. So then we go to another system, which is lithium beryllium. Let's see, can we avoid sodium? So again, the same approach. Full assessment of this lithium beryllium plutonium system. Okay, there is quite huge increase here. So it's like if you're climbing a hill. Yeah, so then the contour lines are either closer or not. So this is also something that you can read directly. But this is the 1.3 mole% pseudo-binary system plotted here. And we found very low melting point, much lower than our criteria, which would be very good. But if you look at the composition axis, this is beryllium. So there will be very high concentration of beryllium. And I told you that's a problem with viscosity. So that's okay for melting, but not practical. So we also say in that case, no. So we look at sodium beryllium. We get, again, the phase diagram. Okay, we don't have to go back to that. So this is the picture we should be looking at. And we find quite low temperature melting point with fairly low amount of beryllium fluoride. So 22, 20, 28 more %. That will be still in the region where the viscosity is not so huge. But still, strictly speaking, I mean, this temperature is, I mean, it could be questionable, but higher than our criteria. So if we would be very strict, we would have to say also no to this system. So that leaves us to the actually quaternary system, so to the ternary metrics. But again, with the phase diagram, with the thermodynamic database, we can plot the phase diagram. This is a quaternary system, but of course, if you have quaternary system, it's graphical representation cannot be done so simply on a paper. So what we did in this case is we directly constrained the plutonium trifluoride to 1.3 molar%. So this is lithium. This is actually lithium sodium beryllium system everywhere containing 1.3 molar% of plutonium trifluoride. So every temperature you look at in this triangle already considers this concentration criteria for plutonium trifluoride, and then every let's say identified lowest this is environment equilibria, eutectic and again eutectic. So these temperatures are the low temperatures identified, and the lowest is this eutectic at 775 Kelvin, which is corresponding to this composition, and that would be the suggestion from a point of view of thermodynamics for proposed fuel. And that's also not very far. There are some deviations, but it's not very far from what was initially proposed. But of course, I must highlight here it's not only melting point, it's also, as I mentioned, viscosity, neutronics, and other extremely relevant properties. But that is already extremely important or useful tool look and to guide us for optimizing the fuel with respect to melting point. So that's the end of example. And this is the last, let's say, slide of what we can do with the database. So that actually follows up the slide before, where we identify the lowest melting point. We can then calculate various properties, as I showed you on this star thing, phase diagram of lithium thorium fluoride. What all properties we can actually determine from the single point. So this is the calculated vapor pressure of this composition. And what's important is that the boiling point is fairly high. Also, what are the vapor pressures at inlet, outlet, fairly low. So this would be also no problem from a safety point of view or general operation of the phase diagram of the molten salt of the Mozart concept. So that's all I wanted to share with you. I thank you very much for your attention. And I think if there are questions before we head for lunch, I guess there's time. Thank you.